Okay, so hello and welcome back. So in this video we want to talk about capacitors in DC circuits. So we have basically capacitors in DC circuits. So basically capacitors are used, capacitors can be used in AC circuits and also in DC circuits. So about AC, we will talk more about AC in the following chapters of this book. But about DC circuits, that's basically what we are doing now. So a capacitor basically is used basically in a DC circuit mainly. A capacitor is used as a temporary basically battery, for example. As a temporary battery. You know that basically battery is creating some sort of potential difference in a circuit. Now when you have a capacitor, something like this, in a circuit, and suppose that this is, for example, the negative side of the capacitor and this is the positive side of the capacitor. If you charge this capacitor will act as a battery, and then you can basically for example connect this capacitor to some load, for example to some resistor, and then it will, although for a very short time, depending on the value of the capacitance of the capacitor, it will act as a battery temporarily in the circuit, and then it will stop, meaning that the charge stored in the capacitor will be doing some work in the circuit for a few seconds probably, and then it will stop, of course depending on the value of the capacitance, depending on whether the capacitor has been charged fully, and depending on the value of the resistor. Then the time is going to be the time basically is going to be different. So the higher, for example, the resistance of the capacitance of the capacitor here, the longer it will last in the same circuit. The higher the value of the resistance here, the longer the capacitor will last in that circuit. And of course, if your capacitor has not been charged fully, for example only half, then of course it will not it will basically supply some voltage to the circuit probably around half of the time as it would if it were, for example, fully charged, and then it would just simply stop. I mean the charge basically on the capacitor would simply be there would be no potential difference on the two plates of the capacitor, so then there would be no current flowing through the circuit. And now, for example, if you have a capacitor over here, suppose that you have this capacitor and connected to this battery. So you have basically you have this battery over here connected to a resistor, and this resistor is connected to a capacitor, and this capacitor is connected back to the negative pole of the battery. So this is, for example, some resistor, for example 10 kilo ohm, and this is some capacitor, for example C is equal to 10 microfarad, and suppose that this is a power supply V of S, 10 volts, for example DC, and this is positive, this is negative. Again, in the capacitor, when you draw your capacitor like this basically there are two poles. The positive side of the capacitor is shown using this straight line segment, and the negative side of the capacitor is shown using this curved line segment. So this would be positive and this would be negative, and as you can see, positive is connected to the positive and negative is connected to the negative. So these kinds of capacitors are basically called polarized capacitors. Polarized capacitors. Now, on the other hand, there is some other sort of capacitor which is called a non-polarized capacitor. So this, when it comes to this sort of capacitor, there is no polarity, and you can connect this capacitor to a DC circuit in any way that you want. Either way, it would actually work. Now, if you have this, basically, if you have this capacitor over here in this circuit, so you have a battery over here, you have this resistor over here, and you have this capacitor. If you place a switch over here, somewhere over here, if you place a switch in this circuit, and suppose that the switch is open, as soon as the switch is closed, the capacitor will start charging. And charging the capacitor is nothing but charging the capacitor, meaning creating some potential difference across the two leads of the capacitor, meaning that suppose that your capacitor is basically two plates like this, and these two plates are connected to the two leads that come out of the capacitor. Okay, so suppose that this is, for example, negative, this is positive. Now if I connect this to a power supply, of course the power supply can create the required potential difference, and then this plate will be charged with negative charges, and this plate will be positive. Then what happens once the capacitor is fully charged, you can disconnect the battery, and then you can connect the capacitor, for example, to some load, for example, and then it will act as a battery. But since the amount of charge that you can store on the two plates of the capacitor is limited and usually very low, then the capacitor, then there will be some current flowing through the circuit, of course, but the current is going to flow for just a very short time. Usually, for example, if you short circuit, when you charge a capacitor, if you short circuited using the tip of a screwdriver or something like that, the whole charge of the capacitor will be basically discharged. Will be discharged in just a fraction of a second in the form of an arc, and that would be in the form of an arc accompanied with some heat, and that would be basically the whole charge of the capacitor. But you could not do that sort of thing with the battery. For example, if you have a battery if you had some sort of battery over here, and if you basically positive and negative, if the battery is powerful enough, then if you short circuit your battery, then what happens is that your battery will start probably even catching on fire or exploding or something like that, because the amount of charge stored in the battery is usually much more than the much more than the amount of charge that's usually stored in a typical capacitor. So now coming back to this capacitor, basically this capacitor will be charged up to 10 volts. This capacitor will be charged up to 10 volts. Basically, this capacitor in this circuit would be charged to the voltage, up to the voltage that would appear on the two terminals on these two terminals over here. Suppose that you didn't have the capacitor over here. Suppose you had basically this, you had this open, these two open points over here in the circuit, and suppose you close the switch over here. So then if you close the switch and this part of the circuit is open, the full power supply voltage would appear over here, which would be basically 10 volts. Okay. Now suppose that I instead of the open circuit section over here, I basically put a capacitor over here. I install a capacitor over here. So in that case, since we had 10 volts over here, 10 volts DC, then the capacitor would charge up to 10 volts, and that would be the voltage basically of the capacitor. Now, there is, depending on this resistor that you use in the circuit, and depending on this resistor, there will be some time required for the capacitor to charge fully, and there is some terminology here that you need to be familiar with, meaning that there is something called the charge constant, if I'm not mistaken. Time constant, basically, not the charge constant, but the time constant. The time constant, and there is a couple more words related to the vocabulary of capacitors that you need to learn over here. Now, if you want to know how long it takes to reach this voltage, of 10 volts, how long it's going to take the capacitor to reach the voltage of 10 volts in this circuit, you need to know a couple of things and a graph essentially about basically how the whole thing happens, and we will talk about that shortly. So for example, the application of this would be, for example, back, like, I don't know how they do it these days, but back, for example, back 20 years ago or so, camera flash parts, the flash part of a camera that was basically installed on top of a camera. So this was basically, you usually install a couple of batteries inside the camera, usually four 1.5 volts, 4 1.5 volt, basically AA batteries, usually basically four of those 1.5 volt AA batteries you install into the flash, and then once you turned on the flash would start charging itself. So when the flash starts charging itself, what's happening inside the flash is that basically there was usually a big capacitor inside the flash that would start charging. So once this capacitor starts charging, it's going to take that capacitor some amount of time to fully charge. And then once that capacitor is charged, then basically there was this part in the flash that would, I don't know, using some sort of technology, it would create some sort of basically instant source of light in the flash. So then once you push the shutter button on the camera, then that capacitor would basically discharge into that light mechanism inside the flash, and then you had a flash of light for just probably just a fraction of a second, and that way you would light up your pictures that you took using those old cameras, or old-fashioned cameras, basically. So that's the practical application of for example, such a circuit. You charge up your basically your capacitor, and then you discharge it into something that needs basically a whole amount of charge instantly. Now the problem, for example, over here would be that, for example, when you had 4 of those 1.5 volt batteries, those 1.5 volt batteries, they are capable of basically providing the capacitor with the required amount of charge to drive that basically that part in the flash that basically lights up your pictures. But the problem is that the batteries cannot do it instantly. They usually, it's going to take the batteries some time in order to do that. So what we do is that we take those 4 batteries, we connect them to this capacitor. The capacitor will charge the required amount of charge inside itself, and then that charge is ready to be discharged into the light mechanism of the flash. And then in just a fraction of a second, the whole charge basically stored in the capacitor is discharged into, well, not the whole probably, or probably even so. The required amount of charge will be discharged into that light mechanism inside the flash, and then you will have enough basically electrical or you have enough basically electrical charges in order to light up your pictures properly. So that's basically the application of that sort of thing. Now, of course, there is something called the time constant, or tau, of a circuit. So there is something called the time constant, or tau of a circuit. It's usually written like this. So that is called tau, or basically, to write it properly, that is called, that's a Greek letter, that's the Greek letter tau. So the tau is basically the time constant of a circuit. Now, that formula for the time constant of a circuit, of this type of circuit, is basically tau is equal to R times C. So you can write tau is equal to Tau is equal to R times C. So R is basically the resistor that you use in series with the capacitor, and C is basically the capacitor, the value of the capacitance of the capacitor itself. Okay. Now there's a couple more things here to discuss. Okay, so we said that tau is equal to R times C, and of course you know that R has to be in ohms and C has to be in farads, not in any other units. Otherwise you would get your tau in some other unit, and tau is basically the unit for tau. I suppose it doesn't have any units, or it is in seconds basically, because of the because if you go into the physics of a resistor and a capacitor and so on and so forth, and the electric charges and everything related to this formula, if you cancel out all of the units related to R and C, then eventually you will get your tau as in basically in seconds. But we are not going into the physics of this right now. We are just going to use it as it is, and then later we will get into the physics of the electric charges and resistors and capacitors, and well, then into electronics basically. So now to answer the question, what is the formula for the time constant of this type of circuit? So this is the time constant of this type of circuit. Tau is equal to R times C. And the time constant the time constant for this particular circuit would be tau is equal to basically R, which is basically 10 kilo ohm. So you write it as 10 into 10 raised to the power 3 ohm into R, which is into C, which is 10 microfarad. So 10 microfarad would be 10 into 10 raised to the power negative 6 farad. And then you would get this in 10 raised to the power negative 3 times 10 raised to the power, that's 10 raised to the power negative 1 second, which is basically 1/10 of a second. One tenth of a second would be 100 milliseconds. Would be 100 milliseconds. So that would be 100 milliseconds. Now, so 1/10 of a second. Now, the third part of this this question is how long does it take the capacitor to reach 10 volts? So to reach the full basically supply voltage, it takes your resistors 5 time constants. So it takes your resistor your capacitor. It takes your capacitor 5 time constants to reach the full supply voltage, meaning to charge fully, to supply voltage, meaning that it's going to take your capacitor T is going to be equal to, for example, 5 into 10 raised to the power negative 1 seconds, which is equal to which is basically 5 over 10 seconds, which is 1/2 a second, basically 5. That's 1 to 2. That's equal to 1/2 second, or half second basically. So now to what voltage level does it charge in one time constant? Basically in one time constant it's going to charge all the way up to 63% of the supply voltage, and that's basically based on some graph that I will show you shortly. So basically the graph looks something like this, meaning that you have an axis over here which is the percentage of the final voltage. This is the percentage of the final voltage, and this axis over here is basically your time constant. This is your time constant, or tau. This is your time constant, or tau, basically. Now in so you have basically 10, 20, for example, 10, 20, 30, 40, 50, 60, 70, 80, 90, and for example this is 100%. And this is, for example, 1, 2, 3, 4, 5, 6, this is 60%. And so for example around 0.1, 0.2 you're at 10. So if I call this, for example, 1, 2, 3, 4 and 5 time constants, at one time constant you're at 63%, so somewhere around here. At two time constants you're around 85%, so that's somewhere over here. At three time constants you're around somewhere around, I would say, 90% or so, somewhere over here. At four time constants, basically at five time constants you're at 100%. You're at 100%, something like this. And your graph is basically, your graph will be some graph like this. Your graph would be something like this. Now this is 1, this is 2, this is 3, this is 4, and this is 5. So this is 5 time constants. And so basically the question was, how long does it take the capacitor to reach 10 volts? So 10 volts would be basically 5 time constants. And to what voltage level does it charge in one time constant? In one time constant, you see you're at over here, which is 63%. So at one time constant you're at 63% of the final voltage. You're at 63% of the final voltage. So 63% of 10 volts would be 6.3 volts, I suppose. 63% of basically 10 volts would be 63% of 10 volts, which is basically 10. This is 10, 63 divided by 10 is 6.3. So at one time constant, the voltage is at about 63% of the supply voltage, namely 6.3 volts. 6.3 volts. And the full supply voltage was 10 volts basically in this case. So so now one time constant is around, as we calculated here, was basically, we said that basically the circuit was something like this. The circuit was basically this power supply, some resistor and a capacitor over here, and back to the supply, back to the power supply. So the resistor was 10 kilo ohm. The resistor was 10 kilo ohm. The capacitor is 10 microfarad. 10 microfarad. So we calculated the time constant to be 0.1 second. 0.1 second. So we calculated tau to be equal to R times C, and it was 0.1 second. 0.1 second. Now, what that means is that, and then we said that at one time constant, basically when at tau is equal to 1, the voltage of the capacitor V of C is equal to basically 6.3 volts, which is 63% of the supply voltage of 10 volts, basically 63% of 10 volts. So at one time, basically at one time constant, which is in this case basically 100 milliseconds or 0.1 or 1/10 of a second, the capacitor has charged all the way up to 6.3 volts. And then based on this graph, you can calculate the rest of the way, meaning that, for example, at 2 time constants you're around 85%, at 3 around 95%, as at 5 time constants you're at 100%. So that means that this capacitor is going to charge fully in 5 time constants, 5 times tau, to fully charge, and that is basically 5 times 0.1 seconds, which is equal to 5 times 0.1 seconds, which is 0.5 seconds. So that means that in 0.5 seconds your capacitor is going to fully charge all the way up to 10 volts, which is the full supply voltage, 10 volts. So that's basically that. Now, the next question is, the capacitor does not begin charging until the switch is closed. When the capacitor is uncharged or discharged, it has the same voltage on both plates. Of course, if you have a switch over here, if you have some sort of switch over here, then of course when the switch is open, this capacitor is not charging because the circuit is not closed. When you close the switch, the circuit is closed, the current is flowing through the circuit, and so the capacitor is charging. And of course when the capacitor is not charged, it doesn't have any potential difference on the two plates, meaning that it has the same voltage on both plates, meaning that the potential difference is zero. If the voltage here is the same as the voltage over here, then the difference between the two voltages would be, of course, zero. There is no difference between them, so there is no, essentially there is no voltage there. So that is that. Now there is one more thing here, which is basically what is the voltage on plate A and plate B of the capacitor in figure 1.15 before the switch is closed. So the figure, basically that's essentially this circuit over here, and these are the two plates A and plate B of the capacitor. And the question is, what is the voltage on plate A and plate B of this capacitor before the switch is closed. So before the switch is closed, the voltage on these plates is 0, because the capacitor is totally discharged, of course. Now when the switch is closed, of course the voltage on plate A will rise to basically 10 volts, because the capacitor will start charging, and eventually the potential difference between the two plates becomes 10 volts, of course, the supply voltage. And the supply volt and the voltage on plate B, of course it stays at 0 volts, because the voltage on plate B stays at 0 volts. The voltage on plate A will rise to 10 volts, and so the difference of those two voltages would be 10 volts. You could measure that using for example, a voltmeter. And the voltage on plate A again, after, for example, one time constant, as we saw over here, after one time constant over here is basically 63% of the supply voltage. And that you already understand, about 6.3 volts. Now, and I suppose you understand already what this curve basically is. It's some part of a parabola in mathematics. It's called an exponential curve. But of course we are not going to talk about curves and things like that over here unless we had to. Now let's do a couple of examples and see what we have here. So suppose that, for example, you have basically a circuit. Suppose that you have a circuit, a resistor and a capacitor in series, the same as the circuit that we had before. A power supply, a resistor, a capacitor connected back to the supply voltage. This is your R, this is your C, and this is your power supply voltage. You want to calculate the time constant, how long it takes the capacitor to fully charge, and the voltage level after one time constant if a 10 volt battery is used here. Okay, so suppose that, for example, the resistor is 1 kilo ohm. The resistor is 1 kilo ohm, and the capacitor is 1000 microfarad. C is equal to 1000 microfarad. So of course you know that you need to convert this into ohms. So this is 10 raised to the power 3 ohm, and this is basically 1000 into 10 raised to the power -6 farad, which is equal to basically 10 raised to the power -3 farad. 10 raised to the power -3 farad. So that's basically 1,000th of a farad, basically. Now your time constant tau is equal to R times C, which is equal to 10 raised to the power 3 times 10 raised to the power -3, and that is 10 raised to the power 0. That is 10 raised to the power 0, which is equal to 1 second. So that means that your time constant is 1 second. So what that means is that basically we said that in basically when t is equal to when tau is equal to 1 or 1 second, basically your voltage, the potential difference of your capacitor V of C musavi. I'm sorry, I just switched back to Persian. I'm sorry. the potential difference on your capacitor, the potential difference on your capacitor basically reaches 63% of the supply voltage. So 63% of the supply voltage is 63% of for example, and the supply voltage over here is 10 volts. V is equal to 10 volts DC. Okay, so that is 10 volts, and that we already calculated this to be 6.3 volts. Okay, now you want to calculate the time constant, how long it takes the capacitor to fully charge. Now for the capacitor to fully charge, you need 5 time constants. So 5 time constants for the capacitor to fully charge, you need basically 5 time constants. 5 time constants, which is basically 5 times tau, which is equal to 5 times 1 second, which is equal to 5 seconds. That means that it takes your capacitor 5 seconds to fully charge. And the voltage level after 1 time constant, if a 10 volt battery is used, is going to be basically 63%, and we calculated that to be 6.3 volts. Now suppose that we have the same circuit, the same power supply voltage. V of S is equal to 10 volts. V of S is equal to 10 volts, and basically now I change my resistor a little bit. For example, I change my resistor to 330 kilo. 330 kilo, and my capacitor to 0.05 microfarad. C is equal to 0.05 microfarad. So in that case, first you can calculate your time constant here, which is tau is equal to basically R times C, which is equal to 330 kilo ohm, meaning 330 into 10 raised to the power 3 ohm, times your capacitor, which is 0.05 microfarad. So that's 0.05 into 10 raised to the power negative 6 farads, which is equal to basically you have 1 0 here, 2 decimal places, so you get 1 decimal place, and 33 times 5 with 1 decimal place, you get basically 15 1, 15 16 165, 1 decimal place 16.5 times 10 raised to the power negative 3, 16.5 into 10 raised to the power negative 3 in seconds. So that means that your time constant, or tau, is 16.5 into 10 raised to the power negative 3 seconds. You can call this 16.5 milliseconds, because 10 raised to the power negative 3 is basically milli in the SI system, basically. So now the time it takes for the capacitor to fully charge, or basically reach to the full supply voltage, essentially all the way up to here, is 5 time constants. So 5 time constants would be 5 times tau is equal to 5 times 16.5 milliseconds, which is something like 165 times 5 with decimal point, 25.2, 32.3, and 5 and 8, so 82.5 milliseconds. 82.5 milliseconds. Sorry. So it takes your, this is to fully charge. Okay. 82.5 milliseconds. And basically basically how and the voltage level after one time constant. After one time constant, basically we calculated the tau to be 16.5 milliseconds. So meaning that the voltage at when tau is equal to 1, which is equal to 16.5 milliseconds, then V of C, the voltage across the capacitor, is 63% of the supply voltage, which is 10 volts, which is equal to 6.3 volts DC. 6.3 volts DC, which is essentially after 16.5 milliseconds. Okay. Now, okay, so now we have another circuit here. We have a double pole switch. So basically you have this circuit over here. You have the power supply, and then you have basically you have a capacitor here. You have some capacitor here that is connected. You have a capacitor here that basically either goes to, basically your capacitor here is connected to the ground, and over here is basically either connected to a power supply, or to a resistor that goes to the ground. So this resistor goes to ground, meaning that all of these are connected together, or it goes to some power supply, and this is your ground. Okay. Now, then your switch basically can be, this is the common contact of your switch. It's either connected to this or connected here, and you have basically two different positions, X and Y here. So now and of course, for the sake of simplicity, you can connect all of these together to not create any sort of confusion here. You can connect all of these together, all are ground. Now this is your V of S, 10 volts, and this is a resistor 50 kilo ohm, and you have a capacitor 100 microfarad, and you can have your switch in, that's a double pole switch, and it can be either in position X or Y. If your switch is in position X, you can see that the two poles or the two basically leads of your capacitor are short circuited through this 50 kilo ohm capacitor. If the switch is in the Y position, then the negative pole of your capacitor is connected to the negative pole of the power supply. The positive pole is connected to the positive pole of the power supply, and so the capacitor would be charging itself, or would be being charged basically. Now the question here is, with the switch in position X, what is the voltage on each plate of the capacitor? Of course, the voltage on each plate of the capacitor would be 0, because then the capacitor would be practically discharged, because the two leads of the capacitor would be just simply short circuited. So then in that case the voltage across the capacitor would be 0 volts. Now when the switch is moved to position Y, the capacitor begins to charge, of course, through over here connected to the power supply. What is it? What is the charging time constant? So the charging time constant of the capacitor would then simply be basically the switch would be connected here. So that means that then this resistor is not a part of the circuit anymore. And there is another resistor here. I was thinking, so what happens to the resistor in the circuit? So there is another resistor over here, which is a 100 kilo ohm resistor, that is used for calculating the tau of the time constant of your circuit. So we said that tau is equal to R times C, so which is equal to R, which is 100 kilo ohm, 100 into 10 raised to the power 3 ohm, into C, which is 100 microfarad, so 100 into 10 into 10, 100 into 10 raised to the power negative 6 farad, which is basically, this is 10 raised to the power 4, these two multiplied together is 10 raised to the power 4, this is 10 raised to the power negative 3, so that's 10 raised to the power 1, or 10. So that is 10 seconds, which is a long time, really. 10 seconds. So that means that the time constant of your circuit is 10 seconds. 100 microfarad and 100 kilo. Well, your resistor is fairly large, so it takes 10 seconds for basically your time constant becomes 10 seconds, and for the capacitor to be fully charged, then it would take 5 times 10 seconds, which is 50 seconds, around a minute for the capacitor to charge with it. Okay, so now what was it? So when the switching now when the switch is moved to the Y position, the capacitor begins to charge. What is it? The charging time constant, which is basically 10 seconds. Tau is equal to 10 seconds. Now, how long does it take to fully charge the capacitor? To fully charge, you need basically 5 time constants. So 5 time constants would be 5 times 10 seconds, which is equal to 50 seconds. 50 seconds approximately. Now, suppose that basically the next question, so here basically my tau is basically 10 seconds. I'm going to basically erase these so that we have a little bit more space to work. So now suppose that you basically it takes 50 seconds. For example, you moved you set your switch to the Y position, and it takes 50 seconds for your capacitor 50 seconds approximately to fully charge. Now Now suppose that then once you have charged the capacitor, you move the switch back to the X position. So what is the discharge time constant of the capacitor? So since the capacitor is being discharged through this other resistor, which is 50 kilo ohm, then it's going to take half of that time. Basically, it took the capacitor approximately 50 seconds to charge, using a 100 kilo ohm resistor. Now the discharge resistor is 50 kilo ohm, half of that resistor. So it's going to take half of this time to discharge the capacitor, which is going to be basically 25 seconds approximately. So now what is the discharge time constant of the capacitor? The discharge time constant of the capacitor, the discharge time constant of the capacitor is going to be tau is equal to R times C. The same relationship, tau is equal to R times C, which is equal to basically essentially 50 kilo ohms. So 50 into 10 raised to the power 3 ohms times C, which is the same 100 microfarad, 100 into 10 raised to the power negative 6 farad, which is the same thing as that's 10 raised to the power negative 3, 10 raised to the power, well, that's 10 raised to the power 5, that's 10 raised to the power negative 1, and that would be 5 seconds, basically. That would be 5 seconds, discharging through the 50 kilo ohm resistor. So then, since now your time constant becomes 5 seconds, it's going to take, basically in the first example, it took basically our capacitor 5 time constants to charge fully. To fully charge, basically in the first part, we said that to basically fully charge the capacitor, you need 5 time constants. Now, in the second part, to fully basically discharge the capacitor, you need another 5 time constants. But basically using the new time constant that we calculated, because now the resistor has changed, so that the time constant has changed. So then 5 time constants, 5 times 5 seconds would be equal to 25 seconds. And you see that 25 seconds is basically 1/2 of 50 seconds, which is basically this was the time it took the capacitor to charge. And 25 seconds is half of that, and the discharge time, the total discharge time, is half of basically the charging time, because now the capacitor is the value of the resistor is half of the value of the resistor here, basically. So that's basically that. Now there is a couple of things about capacitors that we will still have to discuss, but we will do them in the next video. So I'll see you in the next video.